In this probability video, we're going to talk about what strategies you can use to solve different problems. So often when dealing with probability problems, it is useful to use some form of diagram to help you visualize the situation at hand. Venn diagrams are very popular in dealing with probability. Usually you see problems that only have probabilities and you don't know any context behind them. Tree diagrams are very important when it comes to problems like flipping coins, either one coin 2 times or possibly flipping 3 coins at a time. Also, different word problems are going to be solved using a tree diagram. And then the lattice diagram is when you're rolling 2 dice and you basically are going to list all the possibilities going across 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, 5, 6 from the second die going down. And you basically are using dots to represent each one of those possibilities. So this is what a lattice diagram looks like. So let's talk about some key terms in probability. The first one is complement. The idea of complement is basically the opposite. So here, notice that the apostrophe is being used for complement. So the complement, the keyword is not. So a complement, which is sometimes written A with a little c, means not in A. So a complement is a set of elements that do not belong to set A. In the case of a Venn diagram, if this circle right here represents everything that's in set A, then a complement would be everything that is outside of A. So you would have to shade everything that's outside of A. So that's what your Venn diagram would look like. In terms of a rule, the rule is going to say that the probability of a complement is equal to 1 minus the probability of A. So if the probability that it rains today is 40%, the probability it doesn't rain today is 60%, okay? So 0.4, it will be 0.6. You subtract from 1. Intersection, the keyword intersection is basically and then the symbol is the upside down U. That's from sets. So set A and B is the intersection of sets A and B. So when we talk about the intersection of sets A and B, we're talking about those elements that belong to both set A and set B at exactly the same time. So if you take a look at the Venn diagram, you have 2 overlapping circles. The intersection between those 2 circles is what is referred to as the intersection. It is what they have in common. It is the overlap. So the probability of A and B is the probability that both A and B occur at the same time. Union, the keyword for union is or, and the symbol is A or B, which is the U. So for union, it's basically the elements that belong to A or B or both A and B. So in terms of shading the Venn diagram, what is an A union B would be everything that's in A or everything that's in B or both, everything that's in the intersection. So you would have to shade everything in A, everything in B. So let's take a look, for example, at a random example. Let's say that set A are those students that ate breakfast this morning. And let's say that set B are the students who came to school by bus. If I want to find all the students who ate breakfast and came to school by bus, then we're talking about the intersection of A and B. Those are the ones who ate breakfast and came to school by bus. But if we are saying that we want to find the probability that a student ate breakfast or came to school by bus, then that is a union situation because it is or. So the student could have eaten breakfast, or they could have come to school by bus, or they could have eaten breakfast and come to school by bus. So that's kind of like the way it works. And that's why for or, you shade everything in A, everything in B, including that intersection. There is an addition rule in probability, and that is because we don't want to overcount. So right here in this box, we have the probability of A or B, is equal to the probability of A plus the probability of B minus the probability of the intersection. So let's say that I want to find out how many students ate breakfast or came to school. I would, let's say, go to the classroom and I would ask, raise your hand if you ate breakfast. So then some students would raise their hand. Raise your hand if you came to school by bus. So then I would count out how many students are raising their hand because they came to school by bus. But I can't just add those two together because there could be some students who raised their hand twice because they ate breakfast and they came to school by bus. So I don't want to overcount the number of students. So I'm going to ask, how many of you raised your hand twice? How many of you ate breakfast and came to school by bus? And then whoever raises their hand then, I would go ahead and subtract that amount from my total. Okay, so in probability, you don't want to overcount, so you have to be careful with that. Other important keywords in probability are the words disjoint. The words disjoint mean that set A and set B have no elements in common. They share nothing in common. And in another video, the example I had given you are, let's say in a school, the ninth graders and the seniors. There's no way that a ninth grader is going to be a senior at the same time, or a senior is going to be a ninth grader. There's no way. They're either in ninth grade or they're a senior. So those two sets are disjoint. Another way to describe that is that they are mutually exclusive, meaning they have nothing in common. So because they have nothing in common, the intersection is the empty set. This circle with a line through it is called the empty set. That means they would have no elements in common. In terms of a Venn diagram, if you look, basically nothing would get shaded between both of these because they stand alone. So if you have to shade the intersection, there's nothing to shade because there's no way a ninth grader and a senior are going to be happening at the same time. If you were to walk into a classroom, for example, and you ask students, raise your hand if you're a freshman. Some people would raise their hand. They're in ninth grade. Raise your hand if you're a senior. Other people would raise their hand because they're in 12th grade. Well, how many of you are both in ninth grade and seniors? No one is going to raise their hand because those two events are mutually exclusive. And so if they are mutually exclusive, the addition rule just becomes the sum of those two probabilities together. Let's take a look at some examples. In example 1, notice all we have is the probability of A is 0.6, the probability of B is 0.3, the probability of the intersection is 0.2. So I have no idea what this problem is about. All I see are a bunch of numbers. The strategy to use when you have this situation is a Venn diagram. So I'm going to go ahead and draw two circles. And I'm going to label my circles set A and set B. And then somewhere in a corner, I'm going to put the universe. If I know the intersection, which in this case I do, I want to start with that information and I want to put it in the center, in the overlap between my two circles. Then if the probability of A is 0.6, that means that in this little space right here, which is just A, I'm going to have to take 0.6 and subtract it from 0.2. And so I'm going to get 0.4. So this is 0.4. And the reason is that if I look at all of A, the entire circle, then the entire circle is 0.6. Okay. If I go to the probability of B, the probability of B is 0.3. Because I already have 0.2 in the intersection, I'm short 0.1. And again, if I were to look at the entire circle B, it's going to add up to 0.3. So in order for me to figure out what goes out in the universe, I'm going to have to add 0.4 plus 0.2 plus 0.1, which is 0.7. And then I'm going to do 1 minus 0.7, and that is going to tell me what belongs in the universe. So anywhere in the universe, you want to put what belongs there, which in this case is 0.3. So now we are ready to go ahead and answer the questions. For part A, if I want to find the probability of A union B, if you remember in the Venn diagram, I literally could just shade this together right here. And because it's the shading of all of A, all of B, I can add it all together, 0.4 plus 0.2 plus 0.1, and I know the answer is 0.7. There's also what I like to call math way to be able to do these problems, and that's using the addition rule for probability. So the probability of A or B is equal to the probability of A plus the probability of B minus the probability of the intersection, A intersect B. So the probability of A is 0.6, the probability of B is 0.3, and the intersection is 0.2. So this is 0.9 minus 0.2, which is 0.7, which is exactly the same answer we got when we did it by just shading the Venn diagram. Let's take a look at part B. The probability of B complement. In terms of the Venn diagram, B complement means everything that's not inside of B. So I'm going to outline circle B, and I want everything that's not inside of B. So that is going to be 0.4, and anything that's out in the universe, so it's going to be 0.3 as well. So if I add them together, it's going to be 0.7. Now I'm going to go ahead and do this the math way with the math formula. The probability of B complement is 1 minus the probability of B. The probability of B is 0.3 because remember, B is the entire circle, so the probability of B is 0.3. They also gave it to us in the problem right here. The probability of B is 0.3. And so this is going to equal to 0.7. For part C, it says to find the probability of what is in A and not in B. So this is at the same time. What is going to be in A and outside of B at the same time? So there's only two things right now in A, and that is 0.4 and 0.2. But it says it has to be in A and, because the upside down U is and intersection, at the same time not in B. So the only thing that's not in B is going to be 0.4. So if I had to shade, I would only shade that little piece right there. So the answer is going to be 0.4. So that's how we work with a Venn diagram problem. In number 2, a coin is tossed 3 times. So let's go ahead and create a tree diagram so that we can write out our sample space. So the first time the coin is tossed, it could either land heads or tails. From here, I branch out. The second coin toss can either be heads or tails, heads or tails. The third coin toss can also be heads or tails, heads or tails, heads or tails, heads or tails, which means that my sample space is heads, 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 tails, heads, tails, heads, heads, tails, 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 heads, heads, tails, heads, tails, 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 heads, and tails, tails, tails. So there's 8 possibilities. So part A says, what's the probability of obtaining 3 tails? Only 1 out of 8. The only one that's going to have 3 tails is right here. Then for part B, it says, what's the probability of obtaining at least 1 head? Well, there's 2 ways you can do this problem. At least 1 head, all of them have at least 1 head. The only one that doesn't is the one that is tails, tails, tails. So you can say that it's 7 over 8. Either because you counted all the ones that do have at least 1 head, or you can just say the only way that I'm going to end up with no heads at all is if I have tails, tails, tails. And then you subtract that one case from 8, and then you're left with 7 over 8. In example 3, it says find the probability of getting a sum of 7 on 2 throws of a die. So the strategy in this case is going to be to use a lattice diagram. And we're throwing 2 dice. So the first one is 1, 2, 3, 4, 5, 6. The second one, 1, 2, 3, 4, 5, 6. And then diagonally, I told you that they add up to the same amount. The only way I'm going to get a sum of 7 is 6 and 1, 5 and 2, 4 and 3, 3 and 4, 2 and 5, 1 and 6. So 6 out of 36, which can be simplified to 1/6. I hope you found this video helpful. Remember to subscribe to my channel for more help with math so that you can say, yes, I can do math with confidence. Until next time, thanks for watching.